Today we're going to model some of our trig functions that we worked on modeling on Friday. So similar sinusoidal functions, similar AK DC value, but this time instead of our x representing some kind of rotation or angle, our x might represent something like time. It might represent something like horizontal displacement versus vertical displacement. It just depends on the scenario of the question. So I'm going to show you some different applications of our trig functions not involving angles today. So in this example, we have the height h in meters above the ground of a rider on a Ferris wheel after t seconds can be modeled by this sine function right here. So the difference between, so we did do some Ferris wheel questions on Friday, but our x in those scenarios was actually representing the rotation of the angle as the rider rotated around that Ferris wheel. So this time it's actually tracking the time that it takes them and at what time they're at certain heights. All set? Thanks. Okay, so if I have to graph this function, we have the A, K, D, and C values. We're going to go ahead and just actually do some transformations here. So I'm going to start with the key points of the parent function, which is sine x. So those points were 0, 0, 91, 180, 0, 270, negative 1, and 360, 0. And then we're actually going to do just some transformations. So if I have to graph, there's no need for me to try and interpret anything in particular. I can just literally use my transformations. So we're going to have 10y plus 12 based on our function there. And then I'm going to do reciprocal of k and opposite sign of d. So it'll be 1/3 x plus 30 rather than minus 30. Okay, so we're going to take a quick second and calculate those out. Okay, this is what I got. Correct me if I'm wrong. You guys have the calculators out there. I just did this in my head. Okay, so it looks like the minimum height of the rider above the ground is 2 meters. The max height is 22. We can see that on here. So you'll notice that the minimum point and the maximum point actually transform into the minimum point and the maximum point over here. So that would be a good way, like if something asks you like mins and maxes, just pay attention to where those points get transformed to. So long as our function doesn't have like a vertical flip or anything like that. But normally our application functions won't have negative a and k values. They will be positive for the most part. Thank you. So we're going to go ahead and graph this. I'm just going to make sure that I can get up to 22 on here. So perhaps we would do like 5, 10, 15, 20, and then maybe just like extend this a little tiny bit. And then maybe like this would be our 25. That's easy enough to extend. And then over here, I want to make sure I can get up to 150. So perhaps maybe we add some ticks in here. And maybe we can go by 30s. So we'll do 30, 60, 90, 120, and 150. And then this would be 180, like so. Okay, so we'll just graph our points from here. So at 30, we were at 12. At 60, we were at 22. At 90, we were back at 12. At 120, we're at 2. And 150, we were back at 12. Okay, sometimes I also like to kind of extend this backwards as if it starts at 0, because it might be nice to know like what the starting height is. So we imagine if I'm extending this in the backwards direction, like so, I would be kind of doing the same thing over here. So 0 would actually also be at 2. Okay, because sometimes we like to see like, okay, what's the starting height of the rider at a time of 0? Okay, so technically like this, from 0 to 120 seconds, that's like a full cycle. So do we really need this little part? Probably not really, but we can leave it. It doesn't say like graph specifically 1 cycle, so it should be fine. Okay, so it's important for us to kind of label this is time in seconds. Okay, just so we don't think it's degrees of rotation. And this is height in meters. So we'll make sure that we label our axes. Okay, so actually part B asks us to determine the max and the min, and also the time for 1 revolution and the height above the rider at 30 seconds. So I think we can kind of just observe our graph to figure this out. Go on 2 pages here so we can see. Okay, so max and min. Where are my maxes and mins? What's my max height? 22 meters. Okay, and it happens at 60 seconds. And how about the minimum? 2 meters, and when does it happen?
140 seconds.
Yep. How long does 1 full revolution around the Ferris wheel take?
150 seconds.
You sure? It takes 120, right? So we started at 30 and we ended at 150, so that's 120 seconds that it takes. Okay, and this, I guess, is also 120 seconds and 0 seconds. That's the starting height as well. So we have actually 2 mins that we can see on our graph. And then what is the height of the rider after 30 seconds? Or at 30 seconds, maybe we should say.
11.
We can see it in our points, right? Our points actually tell us
Oh,
that 30 has a height of 12. So at 30 seconds, height is 12 meters. Perfect. Express the equation, the sine equation, from example 1 as a cosine function. We're pretty good at this, right? Where is my nearest? We can actually just use the graph. We don't even have to do any like mathematical calculations. So the rising midline, we can actually see the rising midline right here. And that's why sine has the shift 30 to the right, because the rising midline is 30 to the right. So the only change that I have to make if I want to make this a cosine function is I need to locate that phase shift for the nearest max. So where's my nearest max? So talking like x-wise, like left and right. Right. So it actually occurs 60 to the right. So this would be d of cos right here. Looking for that location of the nearest max, right? So the only thing that I need to change here, no math necessary because we have the graph, is we'll make it t minus 60, because that's the location of the nearest max. Katie?
Is the rising midline just C?
It is the location, so it's on C, but it's the location where we would be going from the midline up into a mountain. So this right here is the rising midline. Joey?
What's the other way we can do it again?
To switch from sine to cosine?
Yeah.
Like if I don't have a graph, you'd be using your little like 90 over k formulas. So this one would be like positive 90 over k plus the existing d of sine shift. But we don't do that if we have a graph where we can actually see where the max is. It's just more work than we need to, right?
On the test, do you give us any formulas?
I will give you like the general skeleton of the like sinusoidal function with AKDC, but you guys need to know like max plus min over 2, max minus min over 2, k over, like 360 over k, or 360 over period, and you need to know that switching formula. Okay, so pretty much no is the answer. All right, I'm going to go off this view. Any questions with this before we move forward? Okay. So this example, we're going to talk about tide, T hours after midnight, so height of the tide. I should probably say in meters. Notice that this is not a circular thing at all. Something that is periodic doesn't necessarily have to be a circular object, like a Ferris wheel going in a circle. It just needs to return to the same values over a regular time interval. So for instance, the temperatures at day X of the year, that actually, because the seasons are always cyclical and they're always kind of returning back to the same temperatures. Now there's of course, some variation, like May 13th every year is not the same temperature necessarily, but we can kind of see that general trend of like up in the summer and down in the winter over a regular time interval. So the seasons are somewhat periodic in that sense, right? They return to the same values over a regular time interval. Every July, we know that the temperature is going to be high, right? So same idea with tides here. So the moon phases, they dictate how the tides are going to come in and out. So these tides are always, because the moon phases always go in a cyclical pattern, these tides are also going to be following that, right? So over a regular time interval, the tides will come in and go out based on what's going on with the pull, the gravitational pull, right? So these types of things like that can be modeled using sine and cosine functions. Can anyone else think of some kind of pattern that is cyclical, that happens along the same timelines all the time? This might be a hard question to ask, like to find people, like to find off the top of your head, but you've got tides, there's seasons. Essay? Yeah, so perhaps like the position of the sun as the earth rotates around it, yep, can be tracked with a sinusoidal function, yep, for sure. That kind of has to do with seasons in a sense, but we can also track maybe like distance from the earth to the sun as the year progresses. It's always the same, right? That's why we have the seasons. Can anyone else think of anything that's like cyclical that happens like along the same time schedule? Maybe. Absences for tests. Student absences versus days of test. No, I'm just kidding. A pendulum, like if you have a pendulum swinging, of course, like we're kind of saying that like the force of friction or the force of like that slows that pendulum down would have to be negligible. But if it were, have you guys ever seen a pendulum like swing on a clock, like a grandfather clock that has like a pendulum, like one of those old clocks? That's actually, it's like, it's powered, right? So that thing swinging back and forth, it's hitting the same heights above the ground at a regular time interval. So pendulums are a good one that can be expressed using sine and cosine functions as well. Okay, so anyways, so we're going to find the max and min values for the depth of the water. So talking about the y's. I think we should be able to find max and min without having to do much work here. If I know the middle of my graph, so the mid height of the tide is 7 meters. That's the C value, right? And the tide is going to go up and down from there. How far up and down is the tide going to go from there? I like your confidence, though. 5, yeah, it's going to go 5 up and 5 down. That's the amplitude. It tells us the distance from the middle to the max and middle to the min. So what is the max tide height? 12 meters. And minimum tide height? 2 meters. Really good. Awesome. So not much calculation needed with that, just kind of using our common sense. So what time is high tide and what time is low tide? That's a little bit more challenging. So we have a couple options here. We can try to plug in 12 and 2 for our height and solve for time. That might be a little bit challenging. Or this idea that I showed you in the first question, where the max and min are actually going to get transformed to the max and min here. Perhaps we can take our max and min points of sine and just perform some transformations on it to see what the x coordinates do. Okay, so that's what I'm going to do. Our parent function here is the sine function. So for part B, I'm going to take the max of sine, which is 91, and the min of sine, which is 270 negative 1. And then we're going to actually perform the transformations on these 2 points. I mean, you could do them all if you wanted to. Thank you. But I think we only really need to see where those maxes and mins get transformed. So I'm going to do 1/30th x plus 5 and 5y plus 7. This side, I already kind of know these values anyways. I expect that I'll get 12 and 2, but I'm just going to make sure that we get 12 and 2 from those maxes and mins, just to give me some confidence that we're finding the right points here. So 1/30th plus of 90 plus 5, that gives us 3 plus 5, which is 8. And when we sub in 1 here, we get 12, which is what we expected for our max. And then 1/30th of 270 is 9, plus 5 is going to give us 14. And when we sub in negative 1 here, we'll get 2. Okay, so what does this mean, 8 and 14? What did we just find? Joey?
The time when it happened.
So what is 14? 2 a.m., p.m.? Okay, so it's kind of like army time, right? When we say 14, this is tracking, T is time in hours after midnight. So what is 8 hours after midnight? 8 a.m., very good. And 14 hours after midnight, this is, so 12 hours after midnight we know is 12 p.m. And then 13 hours after midnight is 1 p.m. and 14 is 2 p.m. So this is 8 a.m., has a max of 12 meters, max tide height, and 2 p.m. has our min tide height of 2 meters. Now we need to make sure, this seems like it's pretty early on in the day, some of these things. We need to make sure that our period does not allow for extra times of high and low tide to be hit in one single day. So the little check that I would encourage you guys to do always, which you kind of have to do, is check what is the period, because it may happen that it hits a max twice in one day and a min twice in one day, or maybe even more than that, depending on what the period is. So if I take my K value, which is 30, and I do 360 over my K value, that should actually give me my period. So 360 divided by 30, what is that? What's our period here? So it's 12 hours. Meaning every 12 hours we're back at the same tide height.
It's gonna happen twice.
It's going to happen twice. So when does my max tide height happen? If it happens at 8 a.m. and the period is 12.
8 p.m.
Okay, so also because of this information, we know that 8 p.m., because the period is 12 hours, every 12 hours we'll have a high tide. So 8 a.m. and 8 p.m. And how about our low tide? 2 a.m., that's right. 12 hours after p.m. So we'll also have a min of 2 meters at 2 a.m.
Does X also mean time?
X? X here, so our T here is like our X, so it's time after midnight, yeah. Okay, what is the depth of the water at 9 a.m.? Any ideas for how we can calculate this last part here?
It could be like 11 meters.
Okay, so we know it's slightly after 8 a.m. and it's going down from the max, of course, so it's going to be probably slightly under 12. How can I calculate for sure?
Put 9 in.
So if I put 9 a.m. is actually 9 hours after midnight. So if I put 9 in for T, that's going to give me the height of the tide at 9 hours after midnight, so 9 a.m. So we're just going to calculate H at 9. Okay. It should be just like a one-line thing. We're just going to calculate it all together in our calculator. So you should just be able, if you have a tiny space to put this line showing that this is, thank you, subbed in, then you can just put equals right at the end there. Okay, so we're going to calculate this in degrees. Make sure you have some brackets in your calculator where there's brackets in your equation. And that should give us the height at 9 a.m. Derek, what'd you get? You didn't? What did you get? Did you calculate?
No. Bonnie's got it though.
Okay.
I got 11.3.
That probably makes sense, right? So Natalie predicted that it was going to be somewhere around 11 because it's coming down from 12 at 8 a.m., right? So 9 a.m. should be just slightly lower than 12.
Go into times.
You can make the signs for the beach. That will be your career with the tides. I don't know if you'd be out on the beach, but... All right, 11.3 meters. That makes sense. Great. Okay, last one of the day. We have a wind turbine, and it has a height of 55 meters from the ground to the center of the turbine. You guys know those like big windmills? So the turbine, no, I'm trying to remember if windmill, are the turbines the ones that, oh no, those are from water. Yeah. So I was just trying to remember if it was like the water one. You know, have you guys ever seen like in the old movies, like in Beauty and the Beast, where they have like a water turbine that's like turning with the water? But yeah, never mind. So like the big windmills, we're going to graph one cycle of the vertical displacement from the ground. I should say from the ground. Let's add that. Of a 10-meter blade turning counterclockwise, assume the blade starts at 0 degrees. So we're going to start it at the positive x-axis is essentially what we're saying. Okay, it is super helpful if you can off to the right, maybe just draw yourself a little picture here. I'm going to draw it below, but you guys have some space off to the right to draw it. Okay, so we're going to draw this. We have the center of a wind turbine from the ground. How high is that? How high is the center? No. Center of the whole turbine. There's blades that come off it from here. 55 meters, yes.
What if we like get this question on a test and we don't know how to answer?
Well, you're going to practice, so. Okay, this is saying that our blade is actually going to start here. Okay, it's going to start at like the positive 0. But we kind of have to imagine, like if this is 10 meters, if this guy kind of rotates up here, what's going to be the highest height that our blade can get to? Yes, so our max is 65 meters. Okay, if it goes up to the top. And what about our min? What if it rotates like all the way around and down here? Okay, so it's going to hit a height of 45 meters at its minimum. Okay, and then eventually it will kind of rotate here as well, but we know that that's of course the same height as its starting height. So those are kind of our positions as we travel along here, right? So we're considering this to be 0 degrees. I need my heights to go between 45, 55, and 65. So when I have a graph kind of already set up like this, sometimes we crunch the y-axis so we don't have to fit all of those, and we just do this. We'll do like a little crunch that says like there's numbers down there, but we're crunching it down so we can just look at maybe like 45, 55, and 65. Okay? So this is going to be height in meters. And This one actually involves degrees, so this one probably fits better in our last unit, our last lesson, but this will be degrees. But most of our applications today are not involving degrees. Okay, and then of course if my blade is going to rotate all the way around, I want to make sure that this guy can go all the way up to 360. So 0, 90, 180, 270, and then up to 360. Okay, so at 0, how high is the tip of our blade above the ground?
45.
Let's look at our picture. It starts here. It's starting at 55, height of 55. Okay.
Wait, how do you know it's starting there?
It says the blade starts at 0 degrees. So maybe I should say more like positive x-axis or whatever. Starts at its mid-height.
Oh.
So at the usual 0 degree position. Okay, so at 0, we're at a height of 55. We are rotating counterclockwise, which means the next position that we rotate up to is going to be up to the max. So how far have we rotated now? 90. And we're at a max height of 65. Okay, and then once we rotate down to our next position, we've now rotated 180. What's our height of that red blade there? 55 again, good. Okay, and then once we rotate around here to the green blade, we've now rotated 270 degrees. What's the height of the, yep, very good. So we're at the min now. And then back up to the starting position. So a full 360 around if we rotate back, and now we're back at a height of 55. So there is the path of our tip of our windmill blade from the ground. Joey. So I would probably start, like if we're talking about time or like degrees of rotation, usually we won't write arrows on this end because we're starting at 0. But we will write arrows off the other end. But if you're just doing regular transformations, you should have arrows on both ends of your graph. Yeah. But like, yeah, especially if we're dealing with time or something, I don't want to go into negative time. So I'll start at 0, and then I'll have an arrow going off the other way. Other questions for this? No? Could you guys make me an equation for this? It can be sine or cosine. I'll let you guys choose. Sine is a good choice. Why would sine be a good choice here? Where's the midline? The midline, the rising midline is actually on 0, so I wouldn't have to worry about a phase shift. Sorry, the word is not coming to me. So let's say this. What is height at x? What would you guys say? What's the amplitude of this function? What's the, yep. So the distance from the mid to the max and mid to the min, that's 10. If we use a sine function, has our period changed from the usual sine function? So usual sine function is 360. This is also 360. Rising midline is on 0, so we can just say x. And do we have a change in the c value shift? Yeah, we do. Where's the new c value? 55. So we'd say plus 55. Right, because this is actually the midline right here. C is at 55 here. So this would actually be the height of my graph.
What's the normal c value?
0. Yeah. So for a regular sine or cosine function with no changes at all, C is resting at 0. Awesome.